Find a
Okay, so I think we're
watch
recording
it.
now, so I'm actually going to say words that mean things, or also nice things. Hi, I'm Zach. I think most of you in this room know me. If you don't, I'm a second-year PhD student working with Palmer here. I'm going to talk about my research. This is my first research talk. I've given like cool tutorial talks about things that I already know, but now I'm going to talk about something that I already know because I came up with it, kind of. So.
What should I say? You're not going to say, I'm going to talk about things I don't know.
Yeah, well,
that's the next one.
I already postulated that one of the proofs is true in AGDA today, so I'm already talking about things I don't know for sure. But I'm not going to get to that territory with this. So the title of this talk is Linear Logic is Broken. That's a very inflammatory title, as it may be obvious even to those of you who don't know linear logic. But first, I'm going to make sure that there aren't any of you who don't know linear logic. So the basic idea with linear logic is that, okay, so normally with your logic you have some context gamma, right? We're going to call it gamma, it can be called other things too, it doesn't really matter. But it's either empty or it's a context and a proposition, right? So you can think of it in one sense as like a list of propositions or of assumptions. In traditional logic, or what I'm going to call persistent logic, there are structural rules that hold. So this turns into actually a set of things that are true. Right? You don't care how many of each thing there are, you don't care what order they show up in, whatever. It's just, this conglomeration, that's not a word, that doesn't mean anything. Conglomeration, there we go, of just assumptions that you have about the world. And so there's rules, there's weakening that says, well, if you can prove A, then you can prove A with some superfluous assumption. There's contraction that says if I can prove A with, or I guess I'll say if you can prove C with two assumptions, then you can break it back down to one assumption. And there's exchange, which says you can reorder them, but I won't bother writing that because it's not relevant to this talk. Okay, so these are what are called structural rules. And you can just think of them as things that you can do because you're representing the context as a list instead of an actual set. Linear logic gets rid of these rules. Okay, so these are no longer valid. And the idea here is that instead of a set, this now becomes a multi-set of assumptions. So we care about how many times each assumption occurs in this set. And the goal is to require that we use every assumption exactly once. So for example, normally you could say, well, we have A, B, and C as assumptions, and we can prove A. Right? This holds in persistent logic. This does not hold in linear logic because we have to use B and C as well. In the general case, if B and C are something trivial, obviously it does hold. Does this make sense to everyone so far? Cool. So, I care about this. There's a bunch of connectives in linear logic. I'm going to focus on 3 of them. And so, normally in a logic you have maybe A and B, A or B, and stuff like that. They're actually finer grained in linear logic. So instead we have, let's see, I'll define the grammar here. Our propositions A are 1, which is considered empty truth, 0, which is kind of falsehood, top, which is a weird kind of truth, and then the actual connectives are tensor, with, which is written as an ampersand, and or, which is written as circle plus, or I think it's just called plus actually. So the idea with tensor is that we have A and B at the same time. So we can use some resources to get both A and B. With, we say we can get A and we can get B, but they all use the same resources, so we have to choose which one to get. And A plus B is the same intuition as or, if you're familiar with propositional logic. It says well, we can get A, or we have an A, or we have a B, but we don't know which one. So these are both a kind of choice. It's just that with and, we get to choose, and with plus, someone else gets to choose. The world gets to choose. Everyone following so far? Cool. Let's see, I'm going to now erase this, because I'm trying to stay on this half board. So the rules for these are pretty straightforward, I think. So if we have a tensor B, actually I'll make a brief note of notation quick. So okay, So for those of you who aren't familiar with this kind of syntax, this is what's called an inference rule. The line is the line, I don't know. But the idea is that the stuff above the line are the premises, and the stuff below the line is the conclusion. So here, the rule is called tensor left, and it says if we have, you can read it kind of bottom up, if we have the assumption A tensor B, and we're trying to prove C, then we can decompose that and just put A and B in the context. And then continue trying to prove C. Or read it from the top down, it says if we can prove that gamma A and B proves C, then we can prove that gamma with A tensor B proves C. Okay? And then the right rule says if we're trying to prove A tensor B, we have to prove A and we have to prove B, and they have to split the resources. Right, so you combine this here. This is a multi-set, right? So there's no like weird unioning stuff going on here, right? It says, well, if we can split the context somehow that part of it proves A and the disjoint part of it proves B, then we can prove A tensor B. All right. So the rest of them I'll go through in much less detail. So with left, there's going to be 2 of them. I'll just write one of them for the sake of time. A with B proves C, gamma A proves C. So the idea is you get to choose which one. You can also choose B, obviously, that's the other one. And then the right rule looks a lot like the tensor right rule, except we don't split the context. And then plus looks a lot like or from before. Well, if you've seen the rule for or, I guess. Left rule, so it says, well, if we can prove it with A and we can prove it with B, then we can prove it with A or B, because we have to take both situations into account. And again, there's 2 right rules. I only write one of them for the sake of time. It says if we can prove A, then we can prove A or B. Cool? Cool. So these rules are awful and horribly long. So then, obviously that's not true because people have been using linear logic for a while, but I mean in a very certain sense that linear logic is, well, broken. And the sense that I mean is that, so one of the popular interpretations for linear logic is that it is the logic of resources, of, consumable, exactly one-time use resources. And it makes sense to some extent, right? And, like I said, there's, you can't prove anything if there's extra stuff. You can't get rid of anything. You can't duplicate anything. So, for example, you can't prove. I guess let me go over here. I'm going to keep all my linear logic on one half of the board. So, for example, you can't prove that A entails A tensor A. Right? It's wrong, and it should be wrong, right? Because you can't duplicate it. So you have one A. You have to apply tensor right rule over there. You have to split your context somehow. A can only go towards proving one of the other A's. So you can prove one of them, but then the other one you don't have any resources left, and so you're in trouble. And the same thing, this doesn't go the other way either, right? Because you have 2 A's, you can prove A with one of them, but then you have this other thing kind of hanging out, and you can't just delete that at will. Or can you? More on that in a second. But you can prove A with A. And in fact, you can prove this in both directions. Right, so I'll write the turnstile going both ways to say it's interdirectable. Right, so you can say if I have an A, then I have an A or an A. I get to choose. And moreover, if I have an A or an A and I get to choose, then I can get an A out of it by choosing either one. And then similarly, we have A plus A is equivalent to A. Right, because if I have an A or an A, but I don't know which one it is, then regardless of what I do, I just return the A. And the other way around, I just say, well, it's on the left or it's on the right, it doesn't matter. This is weird. Or rather, you should think that this is weird, right? Because if linear logic is the logic of resources, then we shouldn't be able to duplicate these resources, right? Who says that these tensorial resources are somehow more important than with resources or plus resources? And I guess Girard says that because logic. But this is strange. We can duplicate choice. Essentially, this is saying that weakening and contraction are valid on width and plus, just not on tensor. And if we look at why this might be, well, let's look at this left rule. This left rule is the most important one, in my opinion at least. And it says, well, tensor doesn't really have any interesting meaning, right? It's just the context, right? So the comma is in fact just another form of tensor. It's just, it exists on a different level. And so, once you have the comma, tensor obeys all the same properties that you ascribe to the context. Whereas with and with plus, you don't have that nice property. There's no way to kind of keep track of it. Within the system itself, you just have to say, well, okay, if I can split it up in these nice ways, or if I can make this choice, then I can use the tensor, or the with, or the plus. And that's, I assert that this is bad if you actually want to keep track of all of the resources in your system. Any questions so far? Am I making any sense? Okay, that's good. That's promising. So what can we do?
So, I wanted to ask a question.
Oh yeah, cool.
So, so for the with right rule, so this is interesting because, like, reading it top down, it looks like you're saying that both A and B have to be provable. But reading it bottom up, it looks like you can prove both of them.
Yeah.
But in the same gamma, so is the idea that you actually can't prove both of them because?
Well, yeah, I mean, you can prove. So the idea is that there's always like a vending machine example used for this. So the idea is that if you have $1 and you go to a vending machine, and the vending machine is an awesome vending machine, and you can get Coke or beer, and you really want Coke and beer, but they each cost $1 because it's also a really cheap vending machine. I don't know, it's like PBR. So you can get a Coke. But, and I can show you how to get a Coke, right? You feed it $1 and you get a Coke. Or you can get a beer, right? Because you can feed it $1 and you get the beer. But you can't get the Coke and the beer because you would need $2 to do that. But you need to decide where your dollar is going. Right? So with says, I have enough resources to do both these things, but eventually I'm going to have to choose which one to do. Whereas tensor says, I have enough resources to do both of these things at the same time.
But when I read with bottom up, I get an A and I also get a B. So
right, but you get them with the same resources.
Okay, so that's what I'm asking.
Like,
there's something in there that says you get them with the same resources, and you can only use those resources once.
Yeah.
So
I mean, in theory, you could write this right rule and this left rule for the same connective, and there's nothing stopping you from doing that. It's just that it doesn't obey any reasonable property or any properties that you would want it to obey.
So one of the tricky things here is that there's a kind of deep semantic difference between reading rules top down and bottom up. So in the vending machine example, are you the customer or are you the vending machine? That's the difference between reading them bottom up and top down. So going top down is saying, well, I have this $1 and I want to be able to get whatever I'm going to get out of it. And I can get either one, and I get to make the choice. But going the other way around, as the vending machine, you have to be able to provide that choice to people. So as the vending machine, I must be able to give you an A. Yep. I also must be able to give you a B. So I have to be able to prove both of those things with whatever whatever the resources you give me are.
Yeah, that makes sense. I mean, can it give you an A? Yes, sure can. And can it give you a B? Yes. But it's something about like but with the same resources, both with the same gamma and not disjoint gammas is meaningful here.
Yeah. Well, and the gamma is the $1.
Yeah.
So
Are you implying that we need some sort of side condition where we actually can't have A or B in these rules? Or at least in, for instance, the width rule.
Or to like fix this?
To fix it or to think about it. If you said that, it's often the case that linear logic is used to represent like logic of resources. So think about logic of resources and we think that we have a this, but we have the exact same thing with it.
So
here are you treating it as are these separate instances of resources or are they really the same resource? That's sort of a distinction there.
Yeah, I mean, so there's still like a semantic difference, and in fact the problem is that there is a semantic difference between the type, actually I'll use plus as an example instead of with, but it should follow over to with, it's just plus as a more intuitive example. Right, so the type 1 plus 1 is the type of booleans, right? The type 1 is just the trivial type that you can get whenever you want. In fact, it's equivalent to the empty context here. So you don't, the idea with linear logic is that you can't duplicate or erase anything. But the problem is you can easily write a function, or you can write a proof that 1 plus 1 entails 1, or not do as I write, not as I say. So you can write this proof, and this corresponds to a function that takes an argument as a Boolean and ignores it, which you shouldn't be able to do. And so it's, sure you could put the side condition that, A is not equal to B, but, as I just said, that would keep you from writing semantically meaningful things.
This is a totally different kind of idea than you're arguing here that we're actually, dropping information which we shouldn't be able to do as part of the definition of the logic.
Yeah.
So there's a form of resource loss that is not being captured.
We're not capturing the resource loss on the right-hand side.
Yeah. Well, and in fact, the rules actually have the resource loss baked into them, right? So here you have, gamma A with B entails C if gamma A entails C, right? But you're erasing this B. You're just getting rid of it. And then similarly, over here, if gamma entails A, then gamma entails A plus B. You're creating this B out of nowhere. And that should bother a linear logician, because linear logicians, or at least my straw linear logician.
We have only one here.
Oh, okay. But I assert that linear logicians should not want to create things out of nowhere or destroy them unnecessarily, but you're doing these right here. So tensor is fine, but something is wrong with these rules. So are there any more questions before I proceed to part 2? Cool. So we have a problem. Let's see what's going right with tensor. So I already mentioned that the nice thing about tensor is that it decomposes into the context and in fact obeys all the same rules that the context does. So let's look at our contexts. So before we have that, context is just the empty context or a context with a proposition tacked onto the end of it. That's weird, right? Like why should we look at it like that and implicitly do all these conversions on them kind of behind the scenes? Why don't we have a more detailed form of context, right? So what if we had, instead of this, some like contextual form of 1, right? Because I said that the connective 1 is equivalent to the empty context. So let's have this be, the contextual version of that proposition. I mean, I could call it dot again, but I'm not going to because I think this is a more straightforward reading. And what if we have, well, we can also just put a proposition in a context. And then we can have a context, and I'll put a little hat on the tensor thing for now, I guess. So a context, tensor a context. Right, and so this should be another way of reading, those rules over there. I've just, changed it a bit. So now instead of a list structure, it has a tree structure. And again, we can even write the equivalence rules that, it should obey, or that the linear context should obey, right? And we can say, well, if we have gamma 1 tensor gamma 2, then this is equivalent to gamma 2 tensor, gamma 1, and also associativity, but I won't bother writing that because it's tedious. So we can write the context like this, and so I've just rephrased the linear logic stuff for now. With one important distinction is that if we have all of these rules acting explicitly on contexts, then we need to have some way to get between things. And this is actually, there's a logic called bunched implications that I've gotten a lot of inspiration from, that has this exact same rule, and I've done some more things from it that I'll get into in just a moment. But so we have a rule, I'll call it struct, because it's like the structural rule. It says if gamma is equivalent to delta, and delta entails C, then gamma entails C. Okay, where this equivalence relation is based on all the substructural, or the structural rules on context that should hold. Okay, so here it's associative and commutative, and one is the unit.
Similar to Mohn's ones.
Hmm?
Similar to Mohn's ones.
Not quite.
Commutative ones.
So, eventually,
Well,
kind of.
applied. Well, it's one step
Yeah.
removed from that, but
It's
yes.
closer to various things you get with equality,
Yeah.
like Leibniz equality rewriting.
So we have this, but this is still, again, this is the same logic as before. So we need to do something different to make it actually, preserve all of the resources that we care about. And so what we need to do is we need to find some way to put the other connectives into the context. And actually, like I said, these are, width is kind of sorry, camera guy. So width is kind of an internal choice, right? Like I get to choose. Whereas plus is an external choice. You get to choose. But they're resources, right? They're just resources getting shuffled around. So really there should be no distinction between internal and external choice. It's just a choice that you split on. And the idea is that we just need to make the choice first class. So let's do that. And actually I'm gonna erase the hat because the blue connectives are different from red connectives. Let's just say that. So gamma 1 tensor gamma 2, and then gamma 1 plus gamma 2. And so I'm using the same symbols as over there for legibility's sakes. Bunched implications, the logic I mentioned before, has get a green marker. The same idea with different rules that it obeys. It has the same idea, but it calls this one semicolon and this one comma, and it is illegible. Makes no sense. So I'm going to use the one that's actually possible to read. And we need to add a unit for plus. So fancy bold 0, which I cannot figure out how to write in LaTeX. So here are our connectives.
We should talk later.
Yes. Well, I can, but it's bad. So here are the connectives. And again, we need to define left and right rules, right? So we need to define what to do when we find a connective and what to do when we see a connective. And immediately we have to change our strategy for these. And again, this is they did this in bunched implications and in deep inference and in a few other systems, I'm sure. And so instead of, because there's more than one way of putting things into the context, in the context of this tree structure, the idea is really that whenever, for example, whenever we see, I should find what the propositions are, right? Propositions are now going to be, 0, and 1, and then plus, and times. So I just got rid of the circles. No more circles in propositions. So we need to, so whenever we see, for example, A plus B as a proposition in a tree, we should be able to rewrite that to A circle plus B in the contextual form. Okay, and so we can do this. I'm going to write gamma brackets A plus B to mean some tree gamma where A plus B occurs at some leaf somewhere. Make sense? Or really where this is a subtree. So this entails C. So
It would be a leaf.
Hmm?
It has to be a leaf.
Well, it would be a leaf, but we can, in general, the stuff in the brackets is any subtree. So we see this. Actually, I'll write the tensor version first. So if we see A times B in a tree, we can rewrite it to A tensor B. And go about our merry way trying to prove C. And this makes sense, because before we had basically the exact same rule in linear logic, except it wasn't a subtree, it was just right at the end of the list, because it was a list and we could shuffle it around and do all that nice stuff with it. Whereas here, we say, well, if it occurs anywhere, we can rewrite it like this. And in tensor, here is just our contextual version of the contextual comma over there. So really, this is the same rule that it was before. And I'll call it times left. The interesting thing is that when we write the plus rule, I kind of tipped my hand at this earlier, it's exactly the same. If you can read my handwriting. That's what I get for writing too low on the board. So it's the same rule. It's just saying that whenever we see this plus, we decompose it into the context. Okay? All right. And then in fact, the right rules are very similar. Right? So we say if we have gamma 1 tensor gamma 2, and again, this is the exact same thing that we wrote over there. It's just I replaced the plus with a blue tensor. And we're trying to prove A times B. We say gamma 1 entails A, gamma 2 entails B, and we're done. Right? So this is the times right rule. And then when we see gamma 1 contextual plus gamma 2 entails A plus B, we do the same thing. We split the context. And call it plus right. So there's this nice symmetry here that comes out, I think, necessarily from trying to capture the meaning of propositions inside the context. Right? So trying to keep track of what you can do with all of your resources. And you look at this and you think, well, that's kind of trivial. And in some sense it is. But in another sense, these rules are trivial, but that just means all the meaning is contained elsewhere. In this case, it's contained in this contextual equivalence rule here. And in fact, I should specify it forms, what's a ring? Semi-ring. I always forget. So it's a semi-ring, which means 1 is the unit of times, 0, it's a commutative semi-ring. 0 is the unit of plus. Both of these commute, they're both associative. And importantly, in fact, the most important thing is that times distributes over plus. And that's how you get any interesting computational value out of it, in fact. So this is, it's a small language, and in fact, this is an equivalence relation, right? So we go, if gamma 1 is equivalent to gamma 2, then gamma 2, this is a derived rule, is equivalent to gamma 1.
What connective is that on the right side of the equivalence relation?
They're both tensors.
I was calling it tensor hat before I stopped calling it tensor hat. So these are tensor, right? So this is just the tensor is commutative.
Okay. It looked kind of like a sad face with crying a tear, so.
Well, it's sad that linear logic is just so bad. Linear logic and I are still friends. Yeah.
Will you write up an example of distribution? Because
So distributivity says, we'll erase this because so distributivity says that if we have gamma 1 tensor gamma 2 plus gamma 3, this is equivalent to gamma 1 tensor gamma 2 plus gamma 1 tensor gamma 3.
Doesn't that duplicate gamma 1?
This actually, this segues nicely into my next point, which is that so we want to have some interpretation for what tensor and what plus mean, right? And the idea is that tensor represents a spatial resource, which is exactly the same as it was in linear logic. It's the same resource that linear logic actually cares about. But plus represents a temporal resource, which is a choice, basically. It has like a first-class notion of choice that is actually captured by the logic. And so here, the idea is that if we have gamma 1 and then a choice between gamma 2 and gamma 3, we can push the gamma 1 into the choice and say then we can choose between gamma 1 and gamma 2 or gamma 1 and gamma 3. But it's still equivalent, right? And the important thing is that it's still like computationally or informationally equivalent. It's reversible, right? So we can go this way and we distribute, but we can go this way and we can factor it out, right? So it's duplicating it syntactically, but it's not duplicating it semantically, if that makes sense, right? So it can still only exist in one place. Okay. So that's in fact the important interpretation is that we keep track of not only spatial resources like linear logic, but we keep track of temporal resources now too. So like I said, if we have if A entails B, then we get that B entails A. I am currently mechanizing this lemma in Agda. It's fun. It's actually fun. I'm not actually being sarcastic. But so it is fully reversible. It's actually based on work that Amr and Richard James had done before on reversible commutation in a combinator calculus. So essentially, I've just pushed the combinator calculus into the context there. But we're working on it. I wanted to look at things from a nice sequent calculus perspective instead of a combinatorial perspective. So are there any questions on the blue stuff before I get another marker?
So you can't prove 1 plus 1 entails 1 anymore, right?
Oh, yeah,
So
yeah,
this
yeah.
is one of them, right?
Yeah, right. So the important thing is you can't prove that. So yeah, let's go through that. So if we have 1 plus 1, and we're trying to prove 1, right? So we can apply the left rule, right? It says, well, this plus just turns into another plus. Okay, so that's good. And then, in fact, there's another left rule for 1 that turns the 1 into the contextual 1. Really surprising, I know. So we say 1, and I'll cheat and do both of them at the same time, and then we're stuck, right? Because we can apply, whatever contextual rules we want over here, right? We can try commuting it. We can try adding in some zeros somewhere. We can even try multiplying by some 1s if we feel really daring. But the fact of the matter is, you can never get this down to just 1. So this is not a proof. And actually, possibly more tellingly, the other way is that.
So I think the intuition that essentially if you treat those things as numbers, 2 is not 1, so there's no way you can ever
Yeah.
get one to the other.
Yeah, this is a logic where you cannot prove that 1 equals 2. And normally you can't prove that they're isomorphic, but you can still interderive them. We just get rid of that entirely. In fact, the idea is that every derivation in the language is an isomorphism. I haven't quite built up the machinery to show that yet, but again, it's research in progress. Yeah, so if you try to prove that 1 entails 1 plus 1, you get, well, okay, here, and now you're stuck, right? Because you have a 1 on the left, and you have a plus on the right, and you can't duplicate this in any way to try to get, 1. Well, you need 1 plus 1 on the left, basically, and you can't get it. So there's no way to apply this right rule to split this plus over here and get a 1 on the left and a 1 on the right to apply the 1 right rule. Okay? Yeah.
What is the purpose served by having both the circled and uncircled connectives? I mean, over here it's because some of our connectives don't have a punctuation, don't have a comma to go with them.
Yeah.
But now since you've moved all your connectives, all of them have their own punctuation. And actually, there are versions of linear logic which do this too, and I have the same question with those.
Yeah.
What is the purpose served by having both of them?
So I guess I can't speak for the other versions of linear logic that do it. The reason I did it at first was, so I know, I learned this principle from Frank Fenning. I think he took it actually from Martin Lerf, where the idea is that every rule should deal with only one connective. Right, or rather, at most one connective. You have like structural rules that don't deal with any connectives. But so, for example, when you're defining implication, you don't want to define it in terms of negation and or. Or when you're defining negation, you don't want to define it in terms of implication and false, for example. So every set of rules should only refer to its connective. But you don't care about the contextual connectives. And so you can, so this times turns into this, and then everything else happens over in the context. The other more important reason that I discovered later, and which I suspect is the reason why Frank and Martin Lerf did it, is it lets you actually prove cut elimination.
Oh, okay.
So-
That's a very good reason.
Yeah. So, for example, when you have the
I
structural,
was going to say to Kevin, what's the proof say that these things happen at different times, right? I mean, this is like this
Mhm.
plus turns into this at one time,
Yeah.
and this.
Oh, that makes sense.
And that
Yeah.
gets this gets
That makes a lot of
reshuffled with the
sense.
equivalence rules,
yeah,
and then it turns into the other form.
Mhm.
But cut is important.
Yeah.
Also.
yeah, and so these all just basically turn into lets, pattern matching and stuff.
Hmm.
But yeah, so for example, there's the case in cut where you say, well, delta entails A, and gamma with A entails C because you apply the structural rule. So you have gamma with A is equivalent to some gamma prime that maybe has a bunch of copies of A in it, or maybe doesn't have any, and then the new thing entails C. But if you apply this structural rule here, and you've only defined it on the propositional connectives, then maybe having this A in here allows you to do something that having the delta in it didn't. Whereas if you define everything, or if you define the equivalence relation on the contextual versions of the connectives, and then you require that you apply the left rule before you do any weird shuffling around, then this gets you a kind of parametricity property that says, well, if I could do it with the A in here, then I had to have been able to do it with the delta in here as well. So it allows you this nice phase distinction here that lets you actually prove things that you would want to prove.
Thank you.
Yeah, no problem. Anything else? Before I go on to the third and final phase. Yeah.
Why commutative?
He has a point.
Yeah, no, I mean, I eventually do want to do it non-commutatively, but for now it works well with numbers and our intuition of numbers. There's no.
It works fine with graphs if you make it non-commutative.
Yeah, but I like thinking about numbers more than I think about
Yeah, but graphs are an excellent model.
I don't care.
Screw numbers. Numbers are horrible.
Numbers are, I don't know. I mean, there's no reason aside from I want to think about numbers more than I want to think about graphs or whatever. Yeah, I mean, that would be a perfectly legitimate thing to do. Also, it's closer to linear logic, whereas otherwise I'd have to do ordered logic. And linear logic is broken. It sounds a lot cooler than ordered logic is broken. If only because people actually know what linear logic is. So there's that. But yeah, there's no big reason. There's no technical reason as far as I know of. All right. Cool. So I haven't actually. Yeah, I'm going over here. Sorry. I haven't actually explained why linear logic is broken in any technical sense. Now I will. So, over there we have this nice reversible system. Oh, this part is very much a work in progress. I'm pretty sure it's all true. But I'm working on actually mechanizing things, and I don't believe things until I see a mechanized proof of them. I don't believe things that I say until I see a mechanized proof. Other people will take their word for it.
Do you trust Agda?
More than I trust my hands waving wildly about.
You trust me?
More than I trust my hands waving wildly about. However, I don't trust you when you agree with me based on my hand waving.
So we still don't have an ordering on whether you trust Amr or Agda more.
I probably
I won't ask you to answer
I
that.
probably trust Agda more than I trust people.
Okay.
I trust computers to be precise. I trust people to be innovative, if that makes sense. I don't know. But okay, so over there we have this nice reversible system. Preserves information. So, oh, by the way, I've started calling the stuff over here contextual logic. This is probably a name that's taken because every name ever is taken. But that's what I think of it in my mind as. So there's that. So now I'm going to present contextual linear logic. Where the idea is that we can take that methodology, which I assert is actually a nice general methodology that should work for things other than creating a reversible logic system. Sounds almost like a thesis. So we can take that methodology and apply it to linear logic by just adding some more rules that we don't have in the system yet. So what was the big deal with linear logic before? Well, it doesn't admit weakening or contraction on the context. And all that means is that you don't have contextual rules that say A is equivalent to A tensor A, for example, right? You don't have that. Or really, it would be gamma in the general case, but whatever. But, as we showed, you do have things that let you duplicate and unduplicate, to use a technical term, with and plus, which are the two choice operators. So we do have that, I'll write gamma now. Gamma is equivalent to gamma plus gamma, and gamma is equivalent to gamma with gamma. Okay? So we need to add contextual rules that apply these. And there's a few ways we can do it. The way I really liked was that we can say, well, first of all, I should make a note that we can't actually keep using this equivalence thing anymore, because, do I want you to do it? Well, okay, so linear logic isn't reversible, as I showed a bunch of times earlier on the board. So it doesn't make sense for all of the context transitions to be reversible as well, because otherwise, in at least our heads, we should be able to show that the logic is reversible if the stuff we can do in the context is also reversible. Another failing of linear logic is that all the stuff in the context is reversible. It's kind of misleading if you think about it. So instead of writing this, I'm going to write a little squiggly arrow. And so what I kind of want to be able to write is that gamma can transition to gamma with, is it this way? I think so. Yeah, gamma, and then gamma can transition to like some contextual version of top, which is the unit of width, and that if we have gamma plus gamma, we can transition to gamma, and that if we have contextual 0, we can transition to any gamma, right? And so these kind of nicely model the weakening and contraction rules, right? So this says, we can duplicate this, and then we can also send it to the unit. And this says we can compress this into one thing, and we can get the unit into anything. These also look suspiciously like rules for a monoid and a comonoid, respectively. Kind of-ish, I don't know. The algebraists / category theorists in the room can probably correct me where I'm wrong on that. But it's this nice correspondence, and unfortunately this doesn't work for the exact same reasons that I explained to you just earlier, that we have to have the separation between contextual things and propositional things, which is that these, and in fact this one in particular I'm going to single out, this unifies on two contexts. So if we did apply a cut to a proposition, we could say, for example, if we're trying to prove delta plus A entails A, we could say, well, delta entails A, and A plus A entails A, because A entails A, because we applied that structural rule, and this is true from the identity. But we can't, so this is an application of the cut rule, we can't eliminate this application of the cut rule, because it pattern matches on the context here, but we can't pattern match on the context here. That's bad. So that's the technical reason. I won't ask if that makes sense, because it probably doesn't to people who aren't super familiar with proof theory. But that's the technical reason why these rules, while nice, do not work. So instead, we can write contextual versions of the rules that look a lot like the left rules from before. So we can say, what is it? Well, I won't, it doesn't matter. We can write a thing, and I'm pretty sure it works, but I haven't formally, mechanically proved it yet. But there are transition rules that we can write, and actually these are all derivable from the transition rules that actually do allow you to prove cut elimination. But the cool thing here is now we have a system, and you know what, I'm using fancy notation, so I should probably define it. So gamma, again, we're going to have 1, and we're going to have 0, and we're also going to add in the contextual version of top, the unit of width, which I'll just write as top with a circle. And then we have and we have propositions. And then we have gamma 1 tensor gamma 2. We have gamma 1 plus gamma 2. And I'll write another one that's gamma 1 with gamma 2. So all the rules for tensor and plus are still there, and for 1 and 0. But we add new rules that correspond to the ones that I hinted at that I don't feel like writing out for plus. And we copied most of the rules over for plus, but except for one thing, where tensor distributes over plus, or over width, but not the other way around. You can't factor it out. And that's just to stay consistent with the interactions within linear logic. And so I think there's one other caveat, but I don't remember it off the top of my head. So we can add just all those combinators to linear logic, or to contextual logic to get contextual linear logic. And then suddenly we have a system that doesn't really look very linear anymore, right? Because we have, everything still is fine with tensor, or with what is now times the connective. But we have that, how to phrase it? Yeah, we have these two things that admit weakening and contraction. Right? Like you can write weakening and contraction on plus and on with as derived rules of inference. And so suddenly it doesn't look so substructural anymore. Once you show all of the structure that is actually there with all the connectives, it's just, well, a logic with slightly fewer rules than persistent logic, but with more rules than vanilla contextual logic. So one last thing. Are there any questions about that? Okay, so one last thing, and then I'll wrap it up, is that you can, so you want to chug through the proof, and I've actually, I've outlined the proof, I've even written most of it on paper, I just haven't mechanized it, that, if you can derive something in linear logic, right, so if gamma entails A, then you want to be able to derive, the same thing in contextual linear logic, right? And so, this is the translation of this, but with all of the commas turned into contextual tensors, and this is the translation of the proposition with all the tensors turned into pluses, and so on. So you want to be able to prove that. You're chugging through the proof. It's actually pretty straightforward. And then you get to the structural rule. It says, well, if gamma is or not even equivalent anymore, if gamma transitions to delta, and delta entails A, then gamma entails A. Actually, this might be the other way around, I think, now that I think of it. But so if you have this rule, you want to turn this into inference in the usual presentation of linear logic. And you can. And it involves a very nice lemma that says, if gamma transitions to delta, then, and I'll play a little bit fast and loose with syntax here, then gamma entails the proposition delta. I'll write little corners above it so you can tell it's a proposition and not linear or classical logic. So you get this lemma here, and this is a beautiful, beautiful lemma. Because it states that you can index contextual logic instead of using this transition relation that uses combinators that you don't really want to write. You can just index it with another logic. And that's the logic that acts at kind of like a higher level that lets you translate between contexts. So you can write a linear logic program that rearranges the context however you want, and then you prove stuff with that context. And if you can do that, then you can prove gamma. And that system should be equivalent to contextual linear logic, just with a slightly nicer way of rearranging the contexts. So this is still like a research work in progress. But one of the cool things that I want to investigate is indexing this with various logics to make all of the structure explicit without having to go through the extra tedium of relying on a combinator calculus for everything. So that's that. Are there any final questions? Yeah.
So you said those four rules over there you can actually recover?
Yeah.
So does that not deal with our 1 + 1 entails 1 problem?
Well, I mean, yeah. So you're this is contextual linear logic. So this is meant to use the same techniques as contextual logic to recapture linear logic and to show what's actually going on behind the scenes. So yeah, it's going to have the same problems as linear logic because it is equivalent to linear logic, or at least it proves all the same things. things.
So this takes away capabilities and this adds them back in again.
I would say the other way around. But that's
Well.
just yeah, that is not linear logic, but you can add stuff to make it linear logic.
Okay.
And so, like, for example, if you took the proof of 1 plus 1 implies 1, and you put it in your contextual linear logic, in theory this should expose what's wrong with it. I mean, it seems it just like puts it in a place where we can see why you don't like it.
Yeah, because you have to apply then the weakening or contraction rule on the contextual version of plus to be able to actually prove that. So it relies on the extra mechanisms of weakening and contraction, which ostensibly don't exist in linear logic, but in fact that's only for one kind of resource, when there's 3 kinds of resource.
I should point out that the original version of linear logic and many versions of it is not exactly like your contextual linear logic, but it does have that semicolon comma, so it does have one for both with and times. However, it doesn't have a separate one for plus, although the comma on the right side of the turnstile behaves like plus, and the semicolon on the right side would behave like par, which is the one you skip, right?
Yeah,
so
that makes sense.
Now it doesn't have this stratified where you can reason just about contexts, with the separate kind of implication there. It's just you can reason about contexts for some of the rules, and then some of the rules are reasoning about your actual connectives. It also even has what you're calling contextual version of question mark, which they talk about in discharge form, and you'll see it in the square brackets, and it's that same notion. So you might want to take a look at some of the older ways of presenting linear logic and see how they connect.
Would this be in like Girard or?
Yeah.
Okay.
And Girard hates the semicolon comma too, even though he came up with it. For at least this use of it, maybe somebody else had different use of it. He says that you'd like to keep the comma to still be like times, but it seems like semicolon should be somehow distribute over comma, but not the other way. And then he goes, I don't know. is the sentence he came out about that.
Yeah, I hate that syntax. But yeah, thanks. I'll check that out. I haven't done much work with the modal operators. I've done a little bit of work with the modal operators.
Well, they're designed to put back in the reusable resources in a controlled way. So I mean, if your goal is to make them even less of a sense of reuse, then I don't know that you want them.
Yeah. Though I have a take on box at least, but I can leave that for offline discussions. Actually, I can send you a link to the thing that I wrote about it, because I was tired one night and couldn't sleep until I talked about logic for a while. It was bad. I didn't get much sleep that night. Got a lot of writing done that night, just not sleep. Any other questions? All right, thanks.